Alright, welcome back to the videos. So for now, we're going to start on our controller. And I'm going to make a new folder inside the Bolt folder called controller. We're going to create two scripts to start. One will be called entity behavior injectable, and the second will be our player controller. So like we did with the callbacks, we need to create an injectable version of the entity behavior script. So Bolt has something called Bolt entity behavior, and it accepts one generic parameter t. So what is this doing? It's accepting actually something that should be in a Bolt state. So you could have I entity state. And that would create an entity behavior that is attached to a game object which has an entity state. We want to create one that controls an I player state, but our injectable class, we actually want it to have a generic parameter t, so that we can inject into any Bolt entity behaviors that we want, for any state that we want. And to do so, you need to do a little bit more wizardry, which is to say, well, first of all, we need to also implement the iView interface from Strange. And then we need to say where t is a class and it inherits from Bolt I state. And that'll make sure that t is always a Bolt I state, and it'll allow us to pass this t into this t. It's a little tricky. It won't compile if you don't have this, so make sure you do. And moving on, we're going to go grab the same iView code that we used before. Right out of the view. And we're going to put it into our injectable base class. And I don't even have a class definition, so we'll need to say, what do I do? I don't have a namespace. That's what I'm missing. We need to fulfill some usings. And then it should compile. But instead of doing awake, we want to do it on, we want to register ourselves on the attached method. So attached is a Bolt specific callback that happens on entity behaviors when it's been instantiated by the network. So it's like the constructor for a Bolt entity. It's called on the client, it's called on the server, it's called on everything. And then we need to say, you know, the final try of this is true. And that should get us injections on our player entity. So it has a bit of a problem with this. Not sure why. Oh, cleared up. So must have just needed to recompile. Now let's look at our player controller. Rogue. This will be an entity behavior injectable for the I player state, right? Be the I player state. And what that will allow us to do, well, what we want to do here is just make sure that we get injections. So something we're going to need for sure is the game camera. And we're going to, actually I'm going to add one more thing to our base class, because we want to do stuff on attached, but we're already doing stuff in our base class on attached. So like I did with the callbacks, I'll say create a new protected virtual void on attached. And that'll let us do attached. Nope, just on attached. and that'll allow us to override that. And we're going to send ourselves just a message. If game camera is not equal null, debug log player controller is injected. And we're going to give ourselves an exclamation mark because that's awesome. And we're going to clear up any no block. There we go. We're going to clean up any compilation errors. And we're probably going to need to compile our asset. And if we're lucky, we'll get an injection. It didn't work. And the main reason is that our prefab does not have a controller yet. So we add a controller, and we're actually going to do one other, yeah, that should be fine. There we go. We're injected into our player controller. So that's really nice for us. And now we can just kind of move on to doing the execute loop. So a controller has two parts to it that are overrides that Bolt will call. And one is simulate controller, and the other is called execute command. So we saw much earlier that we created our command asset, and it might have been a little confusing, my rambling about it. Okay, all of our stuff disappeared. But the gist of it was that we had input and we had result. And simulate controller is the function that creates the input, and execute command is the part that creates a result. And we're going to go through this and see exactly how it's done. But first, to go along with this, I'm going to create a player motor that is responsible for dealing with like the pathfinding aspect, and we're going to just separate a little bit of that behavior from the main controller part. But it's a bit silly because this is also going to be an entity behavior injectable for iEntity state, because we need that speed part of the state. We need to know what our speed is so that our player motor can tell us how far we want to move. Okay, so we're going to not implement this yet, but we're going to put some stubs here. And the first stub is public vector3 simulate move. And public float simulate rotation for a vector3 movedir. And then we're also going to implement a function called public void reset state, and that will come from an iPlayer command result, and public void execute move for an iPlayer command input. So we're going to delegate parts of the input and result to our move controller, and that it'll just handle the parts that have to do with the movement. But right now, the way we have it set up, that's everything. So it's going to take care of the movedir, the rotation y, and then the result position and rotation y. If you had something where you had a new property that was called attacking, and you had other stuff to do with attacking, you'd put this in the main controller. But this is the way I implemented it for my more complex controller, so right now we're just going to do it this way as well. And we're going to go back to our controller, and we're going to look at the simulate controller command. Simulate controller method, and we're going to create a new input. So we'll say iPlayer command input equals player command create. And all these things, this interface and this class with this method, all this stuff is compiled for us in the Bolt user DLL by the Bolt compiler when you set up these. So this is all coming from the player command. If we created another thing called, you know, car command or tank command or whatever you might want to command, you can use that and you can compile it into code as well. So our input is going to have two parts. Movedir will be for the motor. Oh, sorry, I didn't grab the motor. So one thing we need is our entity, our player motor, and we'll get that component right away. So we have the motor, and the motor is what simulates the move, and the rotation Y based on that move. And then we go entity, which is the entity that this is controlling, Q input input. Right? So this will add that input to a queue, and this, oh, I've done this in the wrong method, I'm so sorry. We need to move this up to simulate controller. And what this will do is every fixed frame, it will queue up a new input command, and it'll be added to a list, right? And say for about half a second backwards or whatever your ping is, it'll keep those inputs alive until it's been confirmed by a server. So how the loop works is that say you've queued up 5 inputs before you've heard back from the server. And then the server sends you back the first input with a result that it simulated, and we're going to want to reset the motor to that result and then simulate all the previous inputs again. And what that'll do is just it'll always replay from the last confirmed state. And it allows you to do client-side prediction and have it where the client looks like they move instantly, but then if the server says, oh, that wasn't right, it can roll back. And it's just it's really nice to do that client-side prediction. So the next thing to do is execute command, and we'll say var command, and we'll cast the raw command into a player command. And then if the reset state variable is true, that means we just got this result confirmed from the server. So we reset the state of the motor to the command result. And that'll say, hey, go back to this position in rotation, and we'll start from there. Otherwise, it's not resetting, so that means that it's doing the local simulation. If it's, well, it could be two things. If it's on the owner, on the server, then it's doing the input for the first time and doing the official simulation of it. If it's on the client, it could be replaying an input from where it was previously reset, or it could be replaying, or it could be playing the input for the first time as a prediction. So you can tell by going command is first execution. So if it's on the server, this will always be true. It's always only played once on the server. If it's on the client, it could be getting replayed after getting rolled back. So only the first execution on the client you want to do certain things. Like if you have a firing noise, you fire your gun, bop, 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 bop. You only want to play the noise the first time. If you didn't do that, you would be getting the noise played multiple times, or one time each frame until the input has been verified by the server. Okay, so we don't need that though. We're not doing anything with that. We're just saying motor execute move for the command input. And then we're saying command result position is the transform position, and the command result rotation Y is the transform rotation Euler angles Y. So we do our movement, and then we save the result of that movement into the command result. And that's everything. Well, there's one more thing to do in our controller, but we're not there quite yet. First things first, we want to fill out, I loaded another Visual Studio project, my apologies. First things first, we want to finish off our motor. So let's see here. We need two things that we're going to require these components on the entity that we're controlling. The first one is a character controller. The character controller is pretty good, not the best, but it's a nice way to have a collider that's kind of doing the movement for you. And the second thing is a seeker. And that's part of the A-star pathfinding project, and we're going to use it to start out our paths for the controller. We're going to save these. We're going to cache these variables as controller. Sorry, quotation is showing up, and the seeker is seeker. And on awake, we're going to cache those variables as just getting components. And because we've required them, we don't need to worry about them not being there. If you didn't know, require component means that the Unity will add it for you whenever you add this script to something. Okay, so I'm going to add one extra method here, which is public void start path vector3 target position. And this is where we're going to inject the pathfinder, and the first thing we're going to do is get the nearest position, nearest walkable position. Right? So we'll say var nearest, well, it's a vector3, we won't hide that. So vector3 nearest position equals the pathfinder get nearest target position. And like I said, to get nearest hides a lot of that NN constraint stuff, you know, A-star path, active instance. It's cleaner this way. If you finally get to the implementation, you'll see, I think it's a nice way of hiding things. Anyways, the seeker has a method start path. This, you want to go, the parameters for start path are the point you're starting at, this transform position, and then we want to go to the target position, and then we need to add a callback, which we're going to call onPath complete, and that is another function that'll get called back when we finished finding this path, and it'll give us a path P. So actually finding an A-star path is fairly computationally intensive. So like you don't want to block. It's multi-threaded. This request is multi-threaded. You don't want to block on this request. You want to do it asynchronously and give yourself a callback and say, hey, this path is ready. I mean, it might be in the order of 20 or 30 milliseconds or even lower than that, but that's like one whole frame, right? That's going to cause some noticeable lag every time you're doing it. If you're doing it, and if you stack paths, if you have 5 things finding a path at once and it takes 100 milliseconds, you're going to have a noticeable pause. So that's how this A-star pathfinding works, and it's a simple pattern to finish this off. If P does not have an error, then we're going to save this path. So we're going to say path P and int current waypoint equals 0. And when we get the path, we'll say path. Sorry, we're going to call this path. If P does not have an error, then path equals P. We cache this path result, and we set our current waypoint to 1. Now, why not 0? There's not much of a difference, but 0 is actually this transform position. So some funky stuff can happen when you, I just got some funky results when I started from 0 on that first frame where it's checking if it needs to go to the next waypoint or not, and it's just the order that things happen, it has a glitchy first frame. So we're not going to worry about that for now. We're just going to move on. And we will start with the simulate move function. So we'll say vector3 movedir equals vector3 0. So by default it's gonna go nowhere unless you tell it to. If path is equal to null, if we don't have any path to look for, then we can just return 0. And then we're gonna say if is at end of path, and we'll call a function called is at end of path, and we'll say path, we'll clear out the path, we'll null out the path, and we'll say return movedir, which is also 0. Now we need to add this bool is at end of path. And how do we do that? We'll say if path is equal to null, return false. Else return the current waypoint is greater than or equal to path vector path count. So this path class has a list of vector3s called the vector path, and that's just basically exactly what I said. It's a list of vector3s that take you in the order of the path, and you just basically increment the current waypoint through those as you walk through them. Anyways, moving on. Movedir is going to be equal to the path vector path of the current waypoint. So this will give us a vector3 at the current waypoint that we're trying to get to, minus the transform position. And then we're going to normalize it. So that'll give us a vector of length 1, which points from our current position to the current target waypoint. And then we're going to zero out the y, because I find it's better to do these things in 2D. There might be a game that needs this, but our plane is flat, and for this demonstration we're just going to not worry about that. Anyways, moving on. If vector3 distance of the current position plus what we're going to move and the path vector path current waypoint is less than the max waypoint dist, then we're going to increment the current waypoint. So that gives us a lot of errors and it might be a bit confusing, but to clear it up, we're going to set an editor value called public float max waypoint dist, and we'll set it to be 0.15f. And that's basically like you know, if when we move, if we're within a certain distance of the current waypoint. Actually, I don't think we need ooh, that's a tough one. Yeah, if we're within a certain distance of the waypoint, then we're just going to go to the next waypoint. And then all we need to do for the rest of the simulation is return the movedir. Right, so that's what simulate movement is going to do. And as far as simulating rotation, there is some cool stuff you can do to smooth it out, but we're going to start with the most basic implementation that we can. So if we're not rotating at all, then we're going to stay the same, and the same is the transform rotation Euler angles y. And this will kind of look like above. If path is null, return the y rotation. If is at end of path, we'll return rotation y. I'm not even sure if it's possible to hit that bit of code because it gets nulled here, so it'll probably always just hit this, but it doesn't matter. And then we'll take a Quaternion target rotation, and the target rotation will equal Quaternion look rotation for the move dir. And then we only want the y to rotate, so we'll zero out the x and the z, and we'll say y rotation equals target rotation Euler angles y, and return the y rotation. Sorry, rotation y. It's not a new variable, we're just using the same one. So either we stay still and we'll give it our old rotation, or we'll do a look rotation and say, hey, we actually want to be looking this way. I mean, if you're pointed to the right and then you start walking to the left, you instantly want your target to rotate to the left as well. Okay, reset state is really easy. We'll say transform position equals the result position, and transform rotation equals Quaternion Euler 0 result rotation y and 0. So I'll take in just the y rotation angles, give it a new rotation based on those angles. And execute is also fairly straightforward. We'll say controller move input move dir times the state speed, right? This is where we need the state part, and then times bolt network frame delta time. So Unity has a fixed delta time, I think. It might be configurable, but I believe Bolt configures it for you, and you can set up your settings to change whether you want it to your fixed frames. The Bolt keeps track of it in fixed frames, whether you want them to be 30, 60, 100, whatever your tick rate you want. Okay, Quaternion target rotation, and in this one we're actually gonna lerp it a bit, or slurp it, which is Quaternion slurp is like the equivalent for quaternions of vector 3 lerp. Quaternion slurp, and we're going from the transforms rotation to the target rotation, and then bolt network, and then the speed will be 1 times bolt network frame delta time times rotation speed. And rotation speed is another editor setting that we just wanted to, you know, I mean, your game might involve different rotation speeds, but more than likely this is just an editor value that you want to tune. You want to tune this value in the editor to make it look good for your game and how big your entities are. So we implemented the entire player motor, and we implemented the player controller. We only have one thing left to do, which is provide an update method to actually get some ability to create those points from the motor to do the start path from. So what we'll do is we'll say if input get key down, a key code mouse 1. So that's a common to just right click to be able to walk. And we'll say ray equals game camera screen point to ray for the input's mouse position. And that gives us a ray that points for infinity through the game world based on where the mouse is pointing. And that'll hit where basically anywhere on our well, you'll see, we'll pass in the world layer in a second. So if physics raycast ray out hit mathf for infinity, and if we want to do this raycast for movement on the game camera world layer, if the mouse is only, you know, we're only going to send a move, we're going to tell the motor, hey, move here, only if it actually hits something in the world layer. And in that case, we'll say motor start path at the hit point. Good. Okay. Now let's see what happens. Does it all compile? Looks like it all compiles. We've got a null reference exception. It didn't find the motor, so we're just missing a bit of setup on our prefab. I'm going to take this out and do it on here. So we're going to get rid of the capsule collider, and on here we're going to create add component physics character controller, and we're going to add the seeker. We don't need gizmos for that. And we are going to add the player motor. We're going to apply this to the prefab. We're going to compile the assets. And now we should get something a little bit more of a different result. So our player controller is injected. Ooh, we've got a little bit of a glitchy behavior. So wonder why that is. Alright, I'm going to stop the video here, and next time I'll figure out what's going on and hopefully make the last fixes that we need, and then we're going to move on to getting the client running as well in the same game.